hopefully folks can see all this. So I think Charlie stole my thunder a little bit, because it's going to cover a lot of the same topics and same data that he presented. So we'll get through it. But what I did want to do first, before we jump into that, was give a brief overview for folks who didn't get a chance to catch up last time when I presented. Basically, this the proposal here allows developers to eliminate outlier metrics when the user agent is in a non-optimal performance state. And what we've seen is that the data indicates that the delays can happen sort of at any time in the navigation pipeline when the user agent is under load. And we also wanted to avoid being a real-time method to determine if the user agent is in a non-optimal performance state. And so the current state of this is we have all of this code checked in Chromium, and we are currently running an origin trial in Edge. And as a result of that, we have some really good feedback, and we've seen some really good data as a result of this. So at a high level, the feedback is nobody likes the name. There is a concern that as more things get added, that the value of the signal degrades over time. Defining user agent startup from a spec perspective would be difficult. The performance timeline shouldn't be a way to determine or detect information you can't detect in other ways, and that we need to expose this in a privacy preserving way. I've got a link here to the Perf working group where we talked about auxiliary and non-auxiliary data. And then some feedback from the tag was that they are worried that it could possibly introduce a side channel for attacks or user fingerprinting, especially if the user has multiple tabs open during startup, which is like one of the conditions where we would return a high entropy value. So in terms of the proposed changes, one of the things that we're talking about, and certainly open to having conversations about naming here, but we, as part of the feedback and the fact that the value of this degrades over time, that our partners were basically asking, like, well, if it's high, we want to know why it's high. Was it because of CPU? Was it because of this? Was it because of memory consumption? Whatever. And so that sort of led to a conversation around, well, since things like CPU and Compute Observer are a little bit more granular in terms of the metrics that they return, if we wanted to, start including these multiple data sources and have a reason why we're flipping things to high, like maybe it just means that these things should be pulled out into their own individual, properties. And then we did talk about, like, maybe we should expose it off Navigator or performance object, but our partners were at least a little bit unclear in terms of what they would do with that data, like except to capture it and attach it to the navigation object and then pass it on. And then, using differential privacy to help add noise into it. And so since we already have really good data with the system entropy as a baseline, our proposal is that we adopt the differential privacy changes first, run another origin trial, and see how that compares to the current signal that we have, and then look at changing the name after we sort of finalized that. And so then jumping to the differential privacy conversation, the proposal is that we do adopt the randomized response algorithm. And then, I think Charlie covered the algorithm here really well in his slide deck, so I don't necessarily feel like I need to recover it here. But I did want to go and test this locally and see sort of how accurate the responses were. So, I ran a million iterations expecting a high return value, a million iterations expecting a normal return value, and then I ran both of those things 1,000 times each. So, as per the proof that Charlie pointed out, the answer is right 75% of the time. And like, here is the data that proves it. Like, these aren't lines, this is a scatter point graph, but you can see how tightly clustered everything is around it. So the top line here is the number of times that the answer was correct, and the bottom line is the noise that's being added into the system. And so this is the total bucket distribution, but I've broken it down as well. Like, here's what it looks like with the high bucket distribution and low bucket or the normal bucket distribution. And so like, the algorithms that Charlie pointed out and the proofs like all play out in like in the data that I've seen. So I think that's everything.